Hello there. I'm so glad you found your way here tonight. Right now, as you settle in somewhere in the world, winter is already at work. Snowflakes are drifting through silent air. Ice is forming delicate patterns on cold glass. Frozen lakes are creaking in the darkness, and the world is slowing into something still and magical. Winter is more than cold weather. It is a transformation written into the very heart of physics, nature, and life itself. A season where hidden wonders rise to the surface, where stillness carries its own language, and where the world slows enough for its deeper workings to show through. Beneath frost, beneath snowfall, beneath the hush in the air, the earth is busy with processes that are as beautiful as they are surprising. Tonight, we journey into the quiet world of winter. We will explore over 100 soothing facts about the coldest season, from the geometry of snowflakes to the strange sounds of frozen lakes, from creatures that survive by freezing themselves to the hidden life beneath the snow. There is no test at the end, no rush, no urgency, just the gentle unfolding of the frozen world to carry you softly towards sleep. So let your breathing slow, let your thoughts grow quiet, and allow yourself to drift into the peaceful wonder of winter. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the remarkable science hidden within the coldest season. Either way, this space is for you. There is something deeply calming about contemplating winter. Every snowflake, every frost pattern, every frozen landscape carries within it a story millions of years in the making. You are part of that story. The same atmosphere that shapes winter weather surrounds you now. The same physics that builds ice crystals operates in the very air you breathe. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in, let the weight of the day drift away, and let us begin with the first of many quiet truths about winter. Winter is patient beyond measure. Ice grows slowly across still water. Snow accumulates grain by grain. Frost patterns develop over hours. And yet, within all that slowness, there are sudden bursts of wonder. Storms that flash with lightning through swirling snow. Lakes that crack with sudden booming sounds. Creatures that awaken from months of frozen stillness. Tonight, we will wander through this magnificent cold world. We will meet the physics that makes snowflakes unique. We will discover how ice can preserve ancient secrets. And we will uncover truths about winter that may surprise even the most curious minds. But there is no hurry. Winter has been returning to the earth for billions of years. It can continue its quiet work while you rest. Let us begin with the wonders hidden within the cold. Snowflakes can carry microscopic particles from space. Every snowflake begins its journey around a tiny nucleus, often a speck of dust or pollen that water vapor condenses upon high in the atmosphere. Remarkably, some of these nuclei are not of earthly origin, but arrive from space as cosmic dust, microscopic particles that drift through the solar system and filter continuously into Earth's atmosphere. Scientists estimate that thousands of tons of cosmic material enter our atmosphere annually, and some of these extraterrestrial particles become the seeds around which snowflakes grow. When you catch a snowflake on your glove, there is a small chance that you are holding something that formed in the cold reaches of interstellar space before finding its way to Earth. These particles include fragments from asteroids, comets, and even material ejected from other star systems long ago. The journey from outer space to a winter storm may have taken millions of years. Ice crystals forming around cosmic dust link the falling snow to the wider universe in ways both poetic and scientific. Winter connects us, grain by grain, to the cosmos. No two snowflakes share exactly the same structure. The familiar claim that no two snowflakes are alike is supported by the staggering complexity of the conditions each crystal experiences during its fall from cloud to ground. A snowflake may pass through countless variations in temperature, humidity, and air pressure during its descent, with each variable influencing how ice molecules attach and the crystal grows. Even the smallest differences in the path a snowflake takes result in unique branching patterns and surface details. The number of possible arrangements for water molecules in even a simple snowflake vastly exceeds the number of atoms in the observable universe. While very small, simple snowflakes might theoretically match, the elaborate six-armed structures we typically imagine are essentially impossible to duplicate. Researchers who have examined millions of snowflakes have found that even crystals formed side by side develop differently. The uniqueness of snowflakes reflects their individual histories written in frozen water. Every snowflake carries its own story from sky to earth. Frost patterns on windows follow hidden air currents. The delicate fern-like patterns of frost that appear on cold window panes are not random, but follow invisible streams of air movement along the glass surface. As water vapor in indoor air contacts the cold glass, it deposits as ice preferentially along paths where air currents concentrate moisture. Tiny imperfections in the glass, residues from previous condensation, and subtle temperature variations all guide the growing frost into its distinctive patterns. The branching structures resemble those found in many natural systems where growth is governed by diffusion-limited aggregation, a process where particles attach to existing structures in predictable ways. Each window develops its own frost signature based on the unique combination of conditions present. Morning frost paintings are temporary artworks created by the physics of phase transitions written on cold surfaces. As the sun rises and glass warms, these intricate designs melt away, only to return the next cold night with new patterns. Frost on glass is physics made visible. Snow appears white because of how light scatters within it. Individual ice crystals are actually transparent, yet accumulated snow appears brilliantly white because of the way light bounces between countless crystal surfaces before escaping back toward our eyes. When sunlight enters a snowpack, it reflects and refracts off millions of ice grain boundaries, changing direction repeatedly. This multiple scattering causes all wavelengths of visible light to mix together before exiting, and our eyes perceive this combination as white. The same principle explains why sugar and salt appear white despite being made of clear crystals. The deeper sunlight penetrates into snow before escaping, the more scattering occurs, which is why dense, compacted snow can appear slightly blue as red wavelengths are absorbed more than blue. Fresh, fluffy snow reflects up to 90% of incoming sunlight, making it one of the most reflective natural surfaces on Earth. The whiteness of winter landscapes results from physics repeated billions of times at grain boundaries. Snow transforms transparent ice into brilliant white through scattering alone. Frozen lakes can produce deep booming sounds. In the depths of winter, frozen lakes become giant musical instruments, producing deep booming, cracking, and singing sounds that can be heard from considerable distances. These sounds occur when temperature changes cause the ice sheet to expand or contract, creating stress that releases suddenly through cracking. The resulting vibrations travel through the ice and into the surrounding air as eerie tones that range from low rumbles to high-pitched pings. Because ice transmits sound much faster than air, these acoustic events can seem to come from everywhere at once. The phenomenon is most dramatic on clear, cold nights when rapid temperature drops create maximum thermal stress. People walking on such lakes may trigger sympathetic vibrations that ripple outward with otherworldly sounds. Thin ice under tension can produce sounds resembling science fiction laser effects that seem impossibly artificial for natural phenomena. Frozen lakes remind us that even seemingly solid and silent landscapes are dynamic, constantly responding to thermal changes with acoustic expression. Footsteps in cold snow can squeak in ways warm snow cannot. When temperatures drop well below freezing, walking through snow produces distinctive squeaking sounds that are absent in warmer conditions. This occurs because at very low temperatures, ice crystals become too cold to melt slightly under pressure from a footstep. In warmer snow, the pressure briefly melts a thin film of water that lubricates the contact between boot and crystal. When it is too cold for this melting to occur, ice crystals grind directly against each other, producing friction that vibrates as audible squeaks. The precise temperature threshold depends on snow conditions, but typically begins around -10 degrees Celsius. The colder the snow, the louder and more pronounced the squeaking becomes. This common winter experience demonstrates how temperature affects the physical properties of ice at a molecular level. The squeaking of cold snow underfoot is the sound of ice crystals breaking and grinding, rather than sliding smoothly past each other. Winter rivers can temporarily reverse their flow. Under certain conditions during winter, rivers may briefly flow upstream as ice dams and pressure dynamics create unusual hydraulic situations. When floating ice jams against bridges, narrows, or previously formed ice, the backup of water can cause temporary flow reversal in sections upstream of the obstruction. The phenomenon also occurs when ice forms unevenly, creating dams that redirect water in unexpected directions until pressure equalizes or the ice breaks. In tidal rivers, the combination of ice cover and tidal forces can produce particularly complex flow patterns. The physics governing these reversals involves the balance between water pressure, gravity, ice resistance, and the mechanical strength of ice dams. Some river communities have historically monitored for ice dam formation due to the flooding risk that accompanies these events. When the dam eventually releases, water surges downstream with considerable energy. Winter transforms familiar rivers into dynamic systems where the normal rules of flow become temporarily suspended. Cold nights can reshape the chemistry of the air. Winter darkness allows chemical reactions in the atmosphere to proceed differently than they do under the influence of sunlight, fundamentally altering the composition of the air during long cold nights. Photochemical reactions that dominate daytime atmospheric chemistry shut down without solar radiation, allowing different processes to take over. Nitrogen oxides, ozone, and various volatile organic compounds reach different equilibrium concentrations under these conditions. The boundary layer of air near the ground can become decoupled from higher layers, trapping pollutants near the surface in stable inversions. Chemical species that would be rapidly broken down by UV radiation persist through winter nights. The cold itself slows some reaction rates while concentrating reactants in ways that accelerate others. These nocturnal chemical conditions can create morning fog, altered air quality, and unexpected atmospheric phenomena. Winter nights are quiet laboratories where the atmosphere experiments with chemistry impossible during warmer seasons. Winter storms can generate lightning within swirling snow. Thunderstorms are typically associated with summer heat, but winter storms can also produce lightning through a phenomenon called thundersnow, where electrical discharges flash within heavy snowfall. The process requires strong vertical air movement that separates electrical charges between different parts of the storm cloud, just as in summer thunderstorms. Heavy, wet snow and embedded convective cells create conditions where ice crystals and graupel collide and transfer electrical charge. The resulting lightning is often accompanied by immediate, heavy snowfall that muffles the thunder to a dull rumble rather than the sharp crack of summer thunder. Thundersnow is relatively rare, typically occurring only a few times per winter season in regions where conditions align properly. The visual effect of lightning illuminating a dense curtain of falling snow creates an otherworldly atmosphere. Where thundersnow occurs, snowfall rates are often extremely high, sometimes depositing several centimeters per hour. Winter storms can be just as electrically active as their summer counterparts under the right conditions. Fresh snow can reflect most of the sunlight that hits it. Newly fallen snow is among the most reflective natural surfaces on Earth, capable of bouncing back up to 90% of incoming solar radiation. This high reflectivity, called albedo, results from the complex structure of fresh snow crystals that scatter light efficiently at all wavelengths. The reflective property has profound implications for regional and global climate, as snow-covered areas absorb far less solar heat than darker exposed ground. This creates a positive feedback loop where snow helps preserve cold conditions that allow more snow to accumulate. Skiers and mountaineers must account for the intense reflected UV radiation that can cause sunburn and snow blindness even on overcast days. As snow ages, settles, and accumulates dust or debris, its reflectivity gradually decreases, shifting the energy balance toward absorption. Fresh snowfall in early morning can momentarily cool regional temperatures simply by increasing surface reflectivity. The brilliant white of new snow is more than aesthetically pleasing. It actively shapes winter weather patterns. Extreme cold can reveal hidden physics in everyday materials. When temperatures drop significantly, ordinary materials begin to behave in unexpected ways that reveal physical properties normally hidden at room temperature. Rubber becomes brittle and can shatter like glass when bent. Metals contract enough to affect precision machinery and building structures. Certain plastics become so stiff they crack under ordinary stress. Water-based liquids can freeze so rapidly they trap their liquid structure in solid form through vitrification. Batteries lose their ability to deliver power as chemical reactions slow dramatically. Even the speed of sound changes in cold air compared to warm air. These transformations remind us that the properties we consider normal are actually specific to a narrow range of temperatures that humans happen to find comfortable. Winter conditions effectively test materials in ways that laboratories deliberately replicate. The cold serves as a natural physics laboratory, where extremes reveal truths hidden at moderate temperatures. Some snow forms in clear skies without any clouds. On extremely cold days, snow can appear to fall from an apparently cloudless sky through a phenomenon sometimes called diamond dust or clear sky precipitation. This occurs when the air near the ground becomes cold enough for water vapor to deposit directly onto tiny particles as ice crystals, even when no visible clouds are present overhead. The resulting crystals are typically small and flat, catching sunlight to create sparkling effects as they drift slowly earthward. The phenomenon most commonly occurs in polar regions and during extreme cold snaps in continental interiors. Because the ice crystals form close to the ground rather than high in clouds, they fall gently rather than gaining speed during a long descent. Diamond dust can persist for hours when temperature and humidity conditions remain stable, filling the air with glittering particles. This skyborne glitter appears magical, but follows perfectly understandable physical principles. Clear sky snow demonstrates that precipitation does not require the dramatic cloud formations we typically associate with weather. Winter sunsets often display more vivid colors than summer. The brilliant oranges, reds, and purples of winter sunsets frequently exceed the color intensity of their summer counterparts due to several atmospheric factors that strengthen during colder months. Cold air holds less moisture than warm air, reducing the haze that can dull sunset colors. Winter air also tends to be cleaner in many regions, with fewer airborne particles from vegetation and dust storms. The lower angle of the winter sun means light passes through more atmosphere before reaching your eyes, increasing the scattering of blue light and allowing warmer colors to dominate. Additionally, certain cloud types common in winter weather create ideal backdrops for reflecting and amplifying sunset colors. The contrast between cold blue shadows and warm golden light enhances the visual impact of winter sunsets. Clear, cold evenings often provide the best viewing conditions, as dry air allows colors to appear vivid rather than washed out. Winter rewards observers with some of the most dramatic skyscapes of the year. Freezing temperatures can make rubber brittle and metal contract. The mechanical properties of common materials change significantly when exposed to winter cold, with rubber losing its flexibility and metals shrinking measurably as molecular motion slows. Rubber molecules normally slide past each other easily, giving the material its characteristic elasticity, but at low temperatures, the molecules move too slowly to rearrange, making rubber stiff and prone to cracking. This is why car tires designed for summer become dangerous in winter conditions. Metals contract as their constituent atoms vibrate less energetically and occupy less average space, a change significant enough to affect precision engineering and cause gaps to appear at joints in structures. Engineers must account for this thermal contraction in bridge designs, pipelines, and countless other applications. The Challenger Space Shuttle disaster was famously linked to rubber O-rings that failed in cold launch conditions. Winter conditions test the limits of materials designed for comfortable temperatures. Understanding thermal behavior remains essential for safe engineering in cold climates. Winter wind can carry particles higher into the atmosphere. The powerful winds associated with winter weather systems can loft dust, sea salt, pollen residue, and other particles higher into the atmosphere than typical summer conditions permit. Storm systems common to winter generate strong vertical air movements that inject particles well above the boundary layer, where they normally remain trapped. Once elevated, these particles can travel vast distances before settling back to the surface, sometimes crossing entire continents or oceans. Winter storms over the Sahara regularly deposit African dust on European snow, visibly coloring alpine snowpacks. Asian dust, carried by winter winds, has been detected in North American air samples. The particles serve as nuclei for ice crystal formation in clouds, influencing precipitation patterns far from their source regions. This global particle transport connects distant ecosystems in unexpected ways, with minerals from one continent fertilizing soils on another. Winter storms act as atmospheric mixing agents on a planetary scale. Some animals transform their bodies drastically for winter survival. Many creatures have evolved remarkable physiological transformations to survive the challenges of winter, including changes to their metabolism, appearance, and even body composition. Arctic foxes and snowshoe hares replace brown summer coats with white winter fur that provides both camouflage and improved insulation. Some species of frogs and turtles allow their bodies to freeze partially, surviving because specialized proteins protect their cells from ice crystal damage. Hibernating mammals slow their heartbeats from hundreds of beats per minute to just a few, dramatically reducing their energy requirements. Bears can lose a third of their body weight while sleeping through winter, metabolizing fat stores accumulated during autumn. Certain birds grow additional feathers for winter insulation, while others undertake journeys of thousands of kilometers to warmer regions. Cold-blooded animals lower their metabolic rates until spring warmth returns. These winter adaptations represent millions of years of evolutionary refinement for cold season survival. Deep winter lakes can contain layers of water that never mix. Beneath ice-covered lakes, water can stratify into distinct layers of different temperatures and densities that remain separate for the entire winter season. Water reaches its maximum density at approximately 4 degrees Celsius rather than at freezing point, so the coldest water actually rises toward the ice, while slightly warmer water settles to the bottom. This arrangement, called inverse stratification, is opposite to the summer pattern where warm water floats on cold. The ice cover prevents wind mixing, and the stable density gradient prevents convective mixing, so layers remain distinct for months. Different depths can support different communities of organisms adapted to specific temperature and oxygen conditions. Fish and other aquatic life concentrate in warmer bottom waters where oxygen depletion becomes a concern in smaller lakes. Spring ice melt eventually disrupts this stratification, triggering mixing events called turnover. Winter lakes are quietly organized systems of layered water columns. Freezing soil can rise with enough force to move buildings. Water in soil expands when it freezes, and under certain conditions, this freezing can lift the ground surface with surprising force through a process called frost heave. As ice lenses form within soil, they draw additional water toward them through capillary action, growing larger and pushing the overlying material upward. The forces generated can lift fence posts, crack foundations, heave road surfaces into rippled patterns, and shift buildings on their foundations. The problem is most severe in fine-grained soils like silts and clays that hold water effectively and allow capillary movement. Repeated freezing and thawing cycles magnify the damage over time, gradually displacing structures and infrastructure. Engineers in cold regions must install foundations below the frost line where temperatures remain above freezing year-round. The annual frost heave cycle can move surface, object centimeters per year on susceptible soils. Winter cold has the power to reshape landscapes and challenge human construction. Ecosystems remain active beneath deep snow cover. A deep snowpack creates an insulated zone at ground level where temperatures remain near freezing regardless of how cold the air becomes above, allowing biological activity to continue throughout winter. This subnivean zone, the space beneath the snow, hosts small mammals like voles and shrews that remain active through winter, tunneling through the snow and feeding on seeds, roots, and dormant insects. The snow insulates the ground from temperature extremes that would otherwise kill many plants and animals. Predators like foxes and owls must hunt through the snow to reach prey hidden in this zone. Plants continue slow metabolic processes beneath the insulating blanket, preparing for rapid growth when spring arrives. Fungi decompose leaf litter, a process that releases small amounts of heat. Soil microbes continue processing nutrients at reduced rates throughout the cold months. The winter landscape that appears lifeless from above conceals a functioning ecosystem just beneath the snow surface. Snow crystals grow into different shapes based on temperature. The familiar six-sided symmetry of snowflakes takes on dramatically different forms depending on the temperature at which the crystals grow within clouds. At temperatures near freezing, snow tends to form flat plates or simple prisms. Slightly colder conditions around -5 degrees produce elaborate branching dendrites, the classic snowflake shape recognized in winter decorations. Still colder temperatures create hollow columns and needles, while extreme cold produces thin plates again. Humidity also influences crystal shape, with drier conditions favoring simpler forms and higher humidity encouraging more elaborate branching. As a crystal falls through different temperature zones, its shape can change, creating complex combinations of features that record the atmospheric conditions through which it traveled. snow scientists have created detailed charts mapping crystal morphology to temperature and humidity conditions. The shape of snowflakes falling past your window tells stories about the atmosphere miles above. Each storm produces its characteristic crystal type based on cloud temperature. Freezing fog can build ice coatings thicker than the fog itself. When fog forms in temperatures below freezing, the supercooled water droplets can deposit directly onto cold surfaces as ice in a process called rime formation. As wind drives fog droplets against objects, layer upon layer of ice accumulates, eventually building coatings that far exceed the thickness of the original fog. Trees, power lines, and structures can become encased in thick crusts of white ice that grow primarily on the windward side. The resulting formations can be hauntingly beautiful, transforming ordinary landscapes into crystalline wonderlands. However, the accumulated weight can bring down tree limbs and power lines, causing significant damage during severe rime events. The ice growths often take feathery or spiky forms oriented into the prevailing wind direction. Rime ice differs from glaze ice in being white and opaque due to trapped air bubbles between rapidly frozen droplets. Mountain peaks, exposed to persistent freezing fog, can develop rime formations meters thick over the winter season. Winter cold can reveal thermal patterns invisible in other seasons. The temperature differences between objects become dramatically more visible in winter when heat leaks from buildings, underground pipes, and other warm sources create contrast against the cold surroundings. Infrared cameras reveal these patterns clearly, showing heat escaping through poorly insulated windows, walls, and roofs. Even without special cameras, melting patterns on snow-covered roofs indicate where heat is escaping from buildings below. Underground steam pipes, buried cables, and sewers create warm lines visible where snow melts first. Animals leave thermal footprints that can be tracked with the right equipment. The cold acts as a revealer, making energy flows visible that would be impossible to detect in warm weather. Energy auditors prefer winter conditions for identifying building heat loss. The cold landscape becomes a thermal map of hidden warmth sources. Winter makes the invisible visible by providing a cold canvas against which warmth cannot hide. Some insects survive winter by removing water from their bodies. To survive freezing temperatures that would shatter ice-filled cells, many insects have evolved the ability to dramatically reduce their body water content before winter arrives through a process called desiccation tolerance. By moving water out of their cells and into body cavities where it can freeze safely, these insects prevent the ice crystal growth that would otherwise rupture cell membranes. Some species reduce their water content by more than half before entering dormancy. The remaining cellular fluid becomes concentrated with sugars and other cryoprotectants that lower its freezing point, creating a substance that remains liquid at temperatures well below normal freezing. When spring arrives and temperatures rise, the insects rehydrate and resume activity. This strategy evolved independently in multiple insect lineages, demonstrating its effectiveness. Certain beetles, caterpillars, and other insects can survive being frozen solid for months using this approach. Desiccation tolerance represents one of many remarkable solutions to winter's challenges. Snow cover can change the path of storms thousands of miles away. The presence or absence of snow cover influences weather patterns on scales far larger than the snow itself, as the reflective and insulating properties of snow affect heat exchange between the ground and atmosphere. When snow covers large areas, it reflects sunlight that would otherwise warm the ground, keeping the surface cold and influencing the temperature gradients that drive atmospheric circulation. These changes can alter the position and strength of jet stream meanders that steer storms across continents. Scientists have documented connections between Eurasian snow extent and weather patterns over North America, mediated through complex atmospheric teleconnections. Computer weather models must accurately represent snow cover to produce reliable forecasts beyond a few days. The feedback between snow extent and atmospheric circulation can amplify or moderate winter conditions regionally. Snow is not merely a result of winter weather, but an active participant in shaping it. The white blanket participates in determining what weather follows. Winter nights can carry sound much farther than summer nights. On cold winter nights, sounds can travel extraordinarily far distances due to atmospheric conditions that bend sound waves back toward the ground rather than allowing them to disperse upward. When the air near the ground is colder than air aloft, a temperature inversion develops that refracts sound waves downward, trapping them near the surface. Combined with the absence of vegetation that absorbs sound in summer, winter nights can allow conversations, traffic noise, and other sounds to carry for kilometers. Train whistles and church bells heard from unusual distances are common reports during winter inversions. Snow cover both reflects sound efficiently and dampens competing background noise, further enhancing distant sound transmission. The crisp, quiet quality of winter nights results partly from this acoustic clarity. The same inversions that amplify distant sounds can make nearby sounds seem muffled, creating strange auditory experiences. Winter transforms the acoustic landscape as surely as it transforms the visual one. Ice crystals in the air can create halos and pillars of light. When millions of tiny ice crystals float in the atmosphere, they can refract and reflect sunlight or moonlight into spectacular optical displays, including halos, sundogs, light pillars, and arcs of various configurations. The most common halo forms a ring of 22 degrees radius around the sun or moon, created by light passing through randomly oriented hexagonal ice prisms. Sundogs appear as bright spots on either side of the sun when plate-shaped crystals fall with faces horizontal. Light pillars extend vertically above and below bright light sources when flat crystals reflect light like tiny mirrors. More complex atmospheric conditions can produce rare phenomena like circumzenithal arcs, tangent arcs, and multiple intersecting halos. These displays occur most often during cold weather when ice crystals form in the lower atmosphere rather than only in high clouds. Observing these phenomena requires looking toward the sun with appropriate eye protection. Winter skies regularly produce displays that rival any summer sunset in beauty. Frozen oceans can produce sounds that travel long distances. Sea ice covering polar oceans becomes an acoustic environment unlike any other, generating and transmitting sounds that can travel for kilometers through the ice and water beneath. The sounds include cracking, popping, and groaning as thermal stress builds and releases in expanding or contracting ice. Pressure ridges where ice sheets collide produce grinding and rumbling that carries through the frozen surface. These sounds form a complex acoustic landscape that marine mammals have adapted to navigate and communicate through. Seals use the ice-covered water as an acoustic channel for their calls. The crackling symphony of sea ice freezing and breaking has been recorded by underwater microphones monitoring submarine activity. Sound travels faster through ice than through water, creating interesting acoustic effects at ice boundaries. The frozen ocean sings and groans through the polar winter, a continuous performance witnessed mainly by the creatures living beneath the ice. Winter temperatures can shift the boundary between land and air. The interface between frozen ground and the atmosphere behaves differently in winter than in other seasons, with frost and ice creating new transition zones that affect heat exchange, moisture movement, and chemical processes. Frost-penetrating soil creates a boundary layer where where liquid water cannot exist, fundamentally changing how the ground interacts with precipitation. Ice forming on surfaces creates barriers that alter wind patterns, trapping cold air in pockets and creating microclimates. The frozen surface of lakes and rivers effectively removes water from the atmospheric system, reducing evaporation and changing local humidity. Snowpack adds an entirely new layer to the landscape with its own physical properties. The ground surface that represents a simple boundary in summer becomes a complex multi-layered system in winter. These changes affect everything from insect survival to nutrient cycling in soils. Winter redefines the fundamental boundaries of the landscape through the transforming power of cold. Snow can insulate the ground well enough to protect plants. A layer of snow acts as an effective thermal blanket, keeping the soil beneath warmer than the air above and protecting plant roots and dormant organisms from lethal cold. Snow contains large amounts of trapped air between its ice crystals, and air is an excellent insulator that resists heat transfer. Beneath a deep snowpack, ground temperatures typically remain near freezing even when air temperatures plunge far below zero. This protection allows many plants to survive winters that would otherwise kill them, which is why gardeners sometimes worry more about snowless cold snaps than snowy ones. The insulating effect is so reliable that some animals, including grouse and voles, burrow into snow for warmth during extreme cold. Paradoxically, regions with heavy snowfall often have warmer soil temperatures through winter than areas with little snow but similar air temperatures. Snow cover determines which plants can survive at any given location, as surely as summer warmth does. Frozen rivers can crack in patterns that mimic tectonic plates. The ice covering rivers and lakes during winter is not static, but moves in response to thermal expansion, water flow beneath, and mechanical stresses, developing crack patterns remarkably similar to those seen in Earth's crustal plates. Linear cracks form where stress concentrates, then branch and intersect to create polygonal patterns. Pressure ridges develop where ice sheets collide, piling up broken fragments like miniature mountain ranges. Leads of open water appear where ice sheets pull apart, analogous to mid-ocean ridges. The ice responds to mechanical forces through fracture and flow in ways geologists recognize from studying tectonics at far larger scales. Watching ice crack and shift provides a speeded-up demonstration of processes that reshape continents over millions of years. The same physics governing plate tectonics operates at winter pond scale, teaching lessons about Earth's dynamics. River ice becomes a laboratory for understanding how solid materials deform under stress. Winter sunlight reflecting from snow can rival desert brightness. The combination of low-angle winter sun and highly reflective snow cover can create illumination levels approaching those found in the world's brightest deserts. Fresh snow reflects up to 90% of incoming sunlight, compared to perhaps 10% for dark soil or vegetation. When sunlight bounces off snow multiple times between ground and clouds before reaching the eye, the cumulative brightness can become overwhelming. This intense reflected light causes snow blindness in exposed eyes and sunburn on skin that would never burn under overcast skies. Mountaineers at high altitude face particular risk, as thin atmosphere allows more UV radiation to reach the surface, while snow reflects most of it back upward. The dazzling brightness of sunny winter days requires protective eyewear that would seem excessive in other conditions. Photography in snow requires exposure compensation to prevent washed-out images. Winter's white landscape transforms the sun's relatively weak rays into an optical challenge. Cold air can sharpen long-distance visibility far beyond summer. Viewing distances on clear winter days can exceed those possible in summer by dramatic margins because cold air holds less moisture and supports fewer particles to scatter and absorb light. Water vapor in warm summer air creates haze that limits visibility even on apparently clear days to perhaps 10 or 20 kilometers. Cold, dry winter air can allow visibility exceeding 100 kilometers under ideal conditions, revealing distant mountains normally hidden in haze. The cleaner winter atmosphere also allows deeper blue sky colors and sharper contrast between objects and sky. Pilots report significantly extended visual reference distances during winter operations. Astronomers value winter nights for similar reasons, as atmospheric turbulence tends to decrease with cold air. The crisp clarity of winter visibility has nothing mystical about it, but results directly from reduced atmospheric moisture. Cold air acts as a cleaning filter that reveals the world's true extent. Winter cold can slow biological processes to near suspension. As temperatures drop, chemical reactions in living organisms slow exponentially, allowing some creatures to enter states so close to suspended animation that distinguishing them from death becomes difficult. Metabolic rate decreases by roughly half for every 10 degrees Celsius of cooling, meaning a hibernating animal at near freezing temperature may be using energy at less than 1% of its summer rate. Heartbeats that occur hundreds of times per minute in active animals may slow to a few beats per hour during deep hibernation. Breathing becomes so shallow as to be nearly undetectable. Some species tolerate body temperatures barely above their freezing points for months at a time. This metabolic slowdown allows survival through winter on stored reserves that would be depleted in days at normal activity levels. The ability to essentially pause life processes represents one of evolution's most remarkable solutions to seasonal energy scarcity. Winter is a waiting room where time passes slowly for the cold-adapted. Snow layers can store precise records of weather over time. Each snowfall accumulates as a distinct layer in the snowpack, and the characteristics of each layer record the weather conditions that prevailed when it formed and since. Heavy, wet snow compresses differently than light powder. Wind-blown snow packs more densely on certain aspects. Ice crusts mark thaw-freeze cycles. Dust and debris layers track atmospheric transport events. Scientists studying snow stratigraphy can read the winter's weather history by digging pits and examining the layered structure. In glaciers and ice sheets, these layers compact into ice that preserves continuous records spanning thousands of years. Analysis of trapped air bubbles reveals ancient atmospheric composition. Isotope ratios in ice layers indicate past temperatures. The deepest ice cores extend climate records back hundreds of thousands of years, providing irreplaceable data about Earth's past climates. Snow that falls today will eventually add to this archive, recording our era for future analysis. Floating ice sheets can collide and grind like miniature plates. On lakes, rivers, and seas, floating ice behaves according to the same mechanical principles that govern Earth's tectonic plates, colliding, grinding, and building up pressure ridges where sheets meet. When wind or current pushes ice sheets together, the edges crumple and pile into ridges that can extend several meters above the ice surface. Where sheets pull apart, leads of open water appear that quickly refreeze. Rotational forces create circular openings called eddies. The grinding of ice sheet edges produces distinctive sounds and creates zones of broken, piled ice called rubble fields. Ships navigating through pack ice must contend with pressure ridges that can trap or crush vessels. The same processes at vastly larger scales shape Earth's continents and ocean floors over geological time. Watching ice pressure dynamics on a winter lake provides an accelerated demonstration of plate tectonics. The physics of solid materials under stress operates identically at any scale. Winter clouds often contain more ice than liquid water. Clouds that appear identical to summer clouds may have completely different internal compositions during winter, with ice crystals dominating rather than liquid water droplets. At temperatures below -15 degrees Celsius, most cloud water exists as ice, though supercooled liquid can persist to much colder temperatures under certain conditions. The presence of ice changes how clouds interact with sunlight, how precipitation forms, and what phenomena appear in the sky. Ice clouds tend to be thinner and more wispy than water clouds, creating the cirrus formations common at high altitudes year-round and at lower altitudes during winter. Precipitation from ice clouds follows different pathways, with snow crystals growing by capturing water vapor rather than through droplet collision as in rain. The seeding of supercooled liquid clouds with ice crystals triggers rapid precipitation, a principle used in cloud seeding operations. Winter shifts the atmospheric water system toward its solid phase throughout the atmosphere. Cold weather can dramatically amplify certain smells. Our perception of odors changes in cold weather through a combination of factors, including air moisture content, temperature effects on volatile compounds, and changes in nasal function. Cold, dry air carries odors more efficiently in some ways, with less moisture competing for olfactory receptors. Wood smoke and other winter scents can seem particularly strong and distinct in cold air. However, many volatile flavor and fragrance compounds become less volatile at low temperatures, reducing the intensity of some odors. Our ability to detect smells decreases somewhat as nasal tissues cool, yet the reduced background odor of winter can make individual scents more noticeable by contrast. The characteristic smell of approaching snow that some people report may relate to shifts in atmospheric ozone or other subtle chemical changes. Winter creates a distinctive olfactory environment where certain scents dominate and others fade. The smell of a winter evening differs qualitatively from any other season. Frozen lakes can develop mysterious circular patterns. Ice on lakes occasionally forms remarkable circular patterns ranging from small disks to formations dozens of meters across, created by various physical processes operating beneath and within the ice. Ice disks form when rotational currents in rivers or streams spin floating ice, while warm water from below melts the edges into increasingly perfect circles. Ice pancakes develop in wavy water as individual ice pieces repeatedly collide, developing raised rims and rounded shapes. Larger mysterious circles visible on frozen lakes may result from methane or other gases bubbling up from the bottom, or from thermal currents creating organized convection patterns. Some circular ice formations remain unexplained despite investigation. The geometric perfection of these natural formations has prompted speculation ranging from scientific to fantastical. The circles demonstrate that physical processes can create remarkably regular forms without any intentional design. Winter transforms lakes into galleries of accidental geometry. Winter storms can move heat between continents. The massive storm systems that develop during winter move enormous quantities of thermal energy from tropical regions toward the poles, playing a crucial role in redistributing heat around the planet. Each winter storm represents the conversion of latent heat stored in water vapor into kinetic energy of wind, and the thermal energy released when vapor condenses into precipitation. The storms that bring cold conditions to mid-latitudes are actually carrying warmth poleward, even as they bring cold air equatorward in their wake. This heat transport prevents tropical regions from overheating and polar regions from cooling without limit. The energies involved are immense, with major storms moving heat equivalent to the output of thousands of nuclear power stations. Climate scientists study these heat transport patterns carefully because changes could alter regional climates significantly. Winter storms are the atmosphere's primary mechanism for balancing Earth's heat budget. Snow that falls on ocean water behaves differently from land snow. Snowflakes landing on open ocean water face conditions quite different from those falling onto land, and their behavior reveals interesting physics of ice and water interaction. The relatively warm ocean surface melts most snowflakes immediately unless air temperatures are extremely cold or water already at freezing point. When conditions are cold enough, snow can accumulate on the ocean surface, forming slush that gradually consolidates into young sea ice. Salt in seawater complicates freezing, creating channels of concentrated brine within developing ice. The floating slush and young ice dampen waves, creating eerily calm ocean surfaces during snowfall. Snow landing on existing sea ice behaves more like terrestrial snow, accumulating in layers that insulate the ice below. However, ocean ice remains dynamic, moving with currents and winds in ways land snowpacks cannot. Snow on the sea exists at the boundary between two great thermal reservoirs. Winter can create natural lenses of ice that bend sunlight. Clear ice forming under certain conditions can develop curved surfaces smooth enough to focus light, functioning as natural lenses with measurable optical properties. Ice forming on calm water or in sheltered locations may develop smooth surfaces that refract light predictably. Icicles, ice pegs on branches, and ice formations hanging from eaves sometimes create focusing effects visible as bright spots or lines where concentrated light falls. In extreme cases, such ice lenses have been blamed for starting fires when they focus sunlight onto combustible materials. The optical quality of ice depends on purity and formation conditions, with fast frozen ice typically containing bubbles and impurities that scatter light rather than focusing it. Clear ice formed through slow freezing can approach the transparency of glass. These natural lenses demonstrate the optical principles that engineers apply when designing manufactured lenses. Winter occasionally provides accidental demonstrations of focused solar energy. Frozen ground can trap gases that reactivate when thawed. Soil gases including methane, carbon dioxide, and radon become trapped beneath frozen ground during winter, accumulating until spring thaw allows their release. The impermeable layer of frozen soil acts as a cap that prevents normal gas exchange between soil and atmosphere. Decomposition continues slowly in unfrozen soil beneath the frost line, producing gases that cannot escape upward. When the ground thaws in spring, these accumulated gases may release rapidly, creating measurable pulses in atmospheric monitoring. In permafrost regions, organic material frozen for thousands of years contains huge reserves of carbon that could enter the atmosphere if widespread thawing occurs. Methane trapped in frozen hydrates beneath Arctic permafrost and ocean sediments represents another massive reservoir of stored carbon. The spring release of winter-trapped soil gases contributes to seasonal cycles visible in global atmospheric measurements. Frozen ground is not merely a solid barrier, but an active participant in Earth's carbon and gas cycles. Snow grains continue to evolve long after they fall. Once snowflakes land and accumulate, they do not remain static, but continue transforming through processes collectively called snow metamorphism. Sharp crystal edges gradually round off as water vapor moves from point to point within the snowpack. Individual crystals bond together through sintering, the same process used industrially to fuse metal powders. Temperature gradients within the snowpack drive vapor movement that can create faceted crystals, a weak layer structure associated with avalanche hazard. Near the surface, daily temperature cycles cause repeated partial melting and refreezing that transforms light powder into dense crust. Deep layers compact under the weight of snow above, eventually becoming ice if accumulation continues for decades. A snowflake that fell as a delicate branching crystal may end up as a small round grain bonded to its neighbors. The snowpack is not merely accumulated snow, but an evolving material whose properties change continuously. Ice can build delicate structures on plants resembling crystals. When conditions are exactly right, ice can deposit on plants and other surfaces in formations of extraordinary delicacy and beauty, creating natural art that vanishes with the first warmth. Hoarfrost forms when water vapor deposits directly as ice on cold surfaces, building feathery crystals that can grow several centimeters long on branches, grass blades, and other exposed structures. The crystals grow preferentially in certain directions based on molecular geometry, creating the six-fold symmetry characteristic of ice. On cold, calm nights with high humidity, entire landscapes can become encased in these fragile crystal coatings. The formations are extremely light and airy, so different from the dense ice that forms when liquid water freezes. Photographers treasure hoarfrost for its photogenic qualities, though it typically lasts only hours before sublimating or being disturbed. These delicate ice structures transform ordinary vegetation into temporary crystalline sculptures. Winter pressure patterns can shape entire regional climates. Large-scale atmospheric pressure systems that develop during winter can dominate regional weather for weeks or months, determining whether areas experience mild or severe conditions regardless of latitude. High-pressure systems can block normal storm tracks, creating persistent cold or dry conditions beneath them while diverting storms to other regions. The Siberian High, a persistent high-pressure system centered over Central Asia, influences winter weather across much of Eurasia. Similar blocking patterns over Greenland can alter the typical westerly storm track across the North Atlantic. These pressure patterns interact with ocean temperatures, snow cover extent, and stratospheric conditions in complex ways that scientists continue to study. Some winters feature persistent patterns that create extended cold snaps or unusually mild conditions. Other winters oscillate between extremes as pressure configurations shift. Understanding these patterns is essential for seasonal forecasting. Winter pressure systems are invisible architects of the weather we experience. Cold air can create mirages normally seen only in deserts. Mirages are typically associated with hot desert conditions, but cold winter air can produce its own varieties of optical illusions through similar physical principles applied in different directions. When cold air near the ground is topped by warmer air, light rays passing through the boundary bend upward, creating effects opposite to the desert mirage. Objects on the horizon may appear elevated above their true positions or stretched vertically into towering, distorted images. Ships and buildings beyond the normal horizon can become visible when these superior mirages make them appear to float above the Earth's curvature. The legendary Fata Morgana, complex mirage formations that can make distant objects unrecognizable, occur most commonly in polar regions and during winter cold snaps. These cold air mirages have deceived observers throughout history, creating phantom islands and appearing to transform mundane coastlines into fantastic architectures. Winter's temperature inversions can make the impossible appear real. Ice sheets can trap ancient bacteria that wake when warmed. Frozen in glaciers and permafrost, microorganisms can remain viable for thousands or even millions of years, entering a state of suspended animation that preserves living cells until conditions change. When ice samples from deep within glaciers are carefully thawed, scientists have revived bacteria, fungi, and other microorganisms that have not been active since before human civilization began. The cold, dark, low-oxygen environment within ice apparently preserves cellular structures that would degrade quickly under warmer conditions. Some researchers study these ancient organisms to understand the limits of life and to consider possibilities for life preserved in ice on other worlds. As glaciers and permafrost thaw due to climate warming, organisms frozen for millennia may rejoin active ecosystems with uncertain consequences. The ice serves as a biological time capsule, holding snapshots of ancient microbial communities. These frozen archives remind us how interconnected the present is with the deep past. Winter storms can lift tiny particles into the stratosphere. The most powerful winter storms, particularly those associated with intense low-pressure systems, can generate vertical air movements strong enough to inject particles from the surface into the stratosphere, more than 10 kilometers above the ground. This requires exceptional energy, as the stratosphere is normally isolated from the lower atmosphere by a temperature inversion that acts as a lid. Particles reaching the stratosphere remain there for extended periods, slowly spreading around the globe and influencing atmospheric chemistry. Volcanic eruptions are the most dramatic source of stratospheric particles, but major dust storms and extreme weather can also contribute. Once in the stratosphere, particles reflect incoming sunlight, potentially cooling the planet slightly. They also provide surfaces for chemical reactions that can affect the ozone layer. The occasional penetration of powerful storms into the stratosphere connects surface weather to the high atmospheric processes that affect Earth's radiation balance. Frozen soil can preserve animal tracks with remarkable detail. When conditions are right, winter provides an extraordinary medium for recording and preserving animal movements through tracks frozen into soil, mud, and snow. Tracks made in soft ground that subsequently freezes can retain fine details including claw marks, skin texture, and even toe pad patterns. Snow preserves the sequence and spacing of tracks until they melt or are covered by new snowfall. Trackers and scientists can read these frozen records to understand animal behavior, population density, and habitat use. The clarity of winter tracks far exceeds what summer conditions typically preserve, as soft ground often collapses or erodes before tracks can be properly examined. In some cases, tracks have been found frozen into ancient ice, providing direct evidence of animal presence thousands of years ago. Each footprint tells a story of a specific moment in an animal's journey. Winter becomes a recording medium for the movements of every creature that crosses it. Freezing temperatures can make paints and plastics behave unexpectedly. The polymer materials that make up most modern paints and plastics undergo significant property changes at low temperatures, sometimes failing in ways that would never occur under warmer conditions. Paint films can become so stiff that they crack when the underlying material expands or contracts with temperature changes. Plastic bags and containers become brittle and shatter under forces they would easily withstand at room temperature. Rubber seals lose their flexibility and allow leaks. Adhesives may release as their bonding chemistry changes. Manufacturing specifications for paints and plastics typically include minimum application and service temperatures below which normal performance cannot be expected. Products designed for warm climates may fail catastrophically when exposed to winter cold. Understanding these material limitations is essential for engineers designing products for cold environments. Winter tests materials in ways that reveal hidden weaknesses in their formulation. Snow dunes can form and migrate like small desert dunes. In windy winter landscapes, snow accumulates and moves in patterns remarkably similar to sand dunes in deserts, forming ripples, barcans, and linear drift shapes that migrate across the terrain. The physics governing dune formation applies equally to any granular material transported by wind, so snow follows the same rules as sand despite its different properties. Snow dunes range from tiny ripples centimeters high to massive drift formations that can bury buildings. They form preferentially in areas downwind of obstructions and in places where wind accelerates through gaps. The angle of repose, the maximum slope before grains slide, is similar for dry snow and sand, creating comparable dune shapes. Unlike sand dunes that persist for years, snow dunes last only until temperatures rise or stronger winds redistribute their material. The parallel between snow drifts and desert dunes demonstrates the universal principles governing particulate transport by wind. Winter ocean water can separate into brine channels with complex chemistry. As seawater freezes, salt is excluded from the forming ice crystals, concentrating in pockets and channels of increasingly salty brine that remain liquid at temperatures below the normal freezing point of seawater. This brine drainage creates complex three-dimensional networks of channels within sea ice, like an upside-down coral reef of liquid passages through solid ice. The concentrated brine is denser than the surrounding seawater, so it tends to sink when it escapes the ice, carrying cold and salt deep into the ocean. This cold, salty water is among the densest in the world ocean and drives global deepwater circulation patterns. The brine channels host unique microbial communities adapted to extreme cold, high salinity, and limited light. Chemical reactions in brine pockets can produce compounds not found elsewhere in the ocean. Sea ice is not merely frozen seawater, but a complex system with its own internal chemistry. Ice can fracture with the energy of small seismic events. When ice finally breaks under accumulated stress, the resulting fracture can release stored energy comparable to small earthquakes, producing acoustic and seismic waves detectable by instruments far from the source. Large fractures in glaciers and ice sheets generate signals recorded by seismometers worldwide. The cracking of lake ice creates miniature seismic events measurable by sensitive equipment. Ice shelves calving large icebergs produce signals equivalent to magnitude 4 or 5 earthquakes. Scientists use these icequakes to monitor ice sheet stability and glacier dynamics without visiting remote sites. The sudden release of stress through fracture follows the same physics as earthquakes in rock, with similar patterns of foreshocks, main events, and aftershocks. Studying ice fracture provides insights into the mechanics of failure in solid materials generally. The winter world is not silent, but punctuated by ice fracture events of all scales. Winter storms can create rare spherical ice pellets. Under specific atmospheric conditions, winter precipitation can take the form of nearly perfect spheres of clear ice called sleet or ice pellets, formed when raindrops or melting snowflakes refreeze as they fall through a layer of cold air near the surface. The pellets bounce when they hit hard surfaces, producing a distinctive rattling sound on windows and roofs. Their spherical shape results from surface tension forces acting during the refreezing process, the same physics that makes water droplets spherical. Larger pellets may show internal structure where freezing proceeded from outside inward. The conditions required for sleet formation, specifically a warm layer aloft over cold air at the surface, occur most commonly during winter storm transitions from rain to snow. Accumulating sleet creates hazardous ice layers that differ from glaze ice in their granular texture. These frozen raindrops represent precipitation caught mid-transformation between states. Snowpack can hide vast amounts of water that release suddenly in spring. Mountain snowpacks accumulate massive quantities of frozen water over winter, storing precipitation that will release during spring melt and provide summer water supplies for downstream ecosystems and communities. A deep mountain snowpack can hold the equivalent of several meters of liquid water distributed across the landscape. When temperatures rise in spring, this stored water begins melting over a period of weeks to months, feeding rivers and recharging groundwater. If spring warming occurs too rapidly, the release can cause damaging floods as water that would normally trickle out slowly arrives all at once. Snow surveys measuring snowpack depth and water content are essential for predicting spring runoff and managing water resources. The annual cycle of snow accumulation and melt is a critical component of water supply in many regions. Mountain snowpack effectively stores winter precipitation until summer, when it is most needed. This frozen reservoir represents one of nature's most important water storage systems. Frozen lakes can trap methane in clear domes beneath the ice. When methane gas bubbles up from decomposing organic matter on lake bottoms during winter, the bubbles can become trapped beneath the ice cover, creating distinctive white patches where gas accumulates, or even visible domes of ice bulging upward from trapped gas pressure. In clear ice, these methane bubbles can be strikingly visible, frozen in stacked columns where repeated bubble releases followed the same path before becoming trapped. The methane itself remains flammable, and dramatic demonstrations show flames igniting from holes drilled through the ice to release the trapped gas. Arctic lakes above permafrost are particularly rich in methane as ancient organic material thaws and begins decomposing. Scientists monitor these trapped gas bubbles to understand methane emissions from warming northern landscapes. The clear ice of frozen lakes reveals a snapshot of ongoing decomposition processes on the lake bottom. These frozen gas pockets demonstrate the dynamic nature of winter lakes despite their apparently lifeless appearance. Birds adjust their flight patterns based on cold air density. The density of cold air affects how birds generate lift and thrust, requiring adjustments to their flight patterns and energy expenditure during winter conditions. Cold air is denser than warm air, which actually makes flight somewhat easier as wings generate more lift for the same effort. However, cold conditions also demand more energy for maintaining body temperature, partially offsetting any aerodynamic advantage. Strong winter winds can assist or hinder migration depending on direction, and birds time their movements to take advantage of favorable conditions. Some species fly at different altitudes in winter to optimize their passage through varying air densities and wind patterns. The V-formation flight of migrating geese becomes even more energy efficient when air density increases. Birds' lightweight bodies make them particularly sensitive to atmospheric conditions that heavier animals might not notice. Winter flight represents a continuous negotiation between the physics of air and the biology of survival. Winter can change how radio waves travel across long distances. The ionosphere, the layer of electrically charged atmosphere that reflects certain radio frequencies back to Earth, behaves differently in winter than in summer, affecting long-distance radio communication in predictable seasonal patterns. Reduced solar illumination during winter nights allows the lower ionospheric layers to dissipate, changing which frequencies can propagate long distances and at what times. Amateur radio operators and international broadcasters adjust their frequency usage based on these seasonal patterns. Winter darkness at polar latitudes can create unusual propagation paths not available at other times. The aurora associated with winter conditions in polar regions can disrupt radio communications by absorbing or scattering signals. Some very low-frequency radio signals actually travel better in winter when atmospheric noise is reduced. Understanding these seasonal variations remains important for communication systems that rely on ionospheric propagation. Winter changes the invisible pathways through which radio signals travel around the world. Snow can glow faintly under ultraviolet light. Certain compounds present in snow, including organic materials and pollutants deposited from the atmosphere, fluoresce when exposed to ultraviolet light, creating faint glows visible under the right conditions. Natural fluorescence occurs when molecules absorb UV photons and re-emit some of that energy as visible light. Snow containing algae or other biological material may fluoresce due to pigments in the organisms. Anthropogenic pollutants, including certain hydrocarbons and industrial compounds, also fluoresce when deposited in snow. Scientists use UV fluorescence to study pollutant distribution in snowpacks and to trace the sources of contaminants. The effect is typically too faint to see without specialized equipment, though particularly contaminated snow may show visible fluorescence under strong UV lamps. This hidden glow reveals information about the invisible chemistry of frozen precipitation. Snow carries chemical signatures that become visible under the right illumination. Ice crystals inside clouds can float for long periods without falling. The tiny ice crystals that make up high-altitude cirrus clouds and the upper portions of winter storm clouds can remain suspended in the atmosphere for extended periods, slowly growing or sublimating as conditions change. These crystals are so small and light that even weak updrafts keep them aloft. Their settling velocity through still air may be only centimeters per second, meaning that any upward air motion can prevent their descent. Ice crystals may drift hundreds of kilometers horizontally while slowly settling through the atmosphere. This extended residence time allows crystals to experience varied conditions and grow into complex shapes. The persistence of ice clouds affects how much solar radiation reaches the surface and how much infrared radiation escapes to space. Climate scientists study high ice clouds carefully because of their important but not fully understood role in Earth's energy balance. These floating crystals are passengers on the wind, unhurried in their journey toward the surface. Winter temperature swings can carve grooves into exposed stone. The repeated freezing and thawing of water in rock crevices during variable winter weather can split and erode stone surfaces through a process called frost wedging. Water seeping into small cracks expands when it freezes, exerting enormous pressure on the surrounding rock. With each freeze-thaw cycle, the crack widens slightly, allowing more water to enter and freeze during the next cold period. Over many seasons and centuries, this process carves distinctive grooves, splits boulders, and gradually breaks down exposed bedrock. The characteristic angular fragments on mountain slopes called talus are largely produced by frost action. Architecture in cold climates must account for frost damage to stone and concrete. The temperature range around freezing point matters more than extreme cold alone, as multiple freeze-thaw cycles cause more damage than continuous freezing. Winter's daily temperature swings become tools for reshaping the land. Snow cover can shift the reflectivity of large regions dramatically. When snow covers the ground, the surface reflectivity or albedo of a region can change from values below 20% for bare soil or vegetation to values approaching 90% for fresh snow. This dramatic shift affects the regional energy balance, as highly reflective surfaces absorb less solar energy than dark surfaces. The difference is substantial enough to alter local and regional temperatures measurably. As snow cover extends or retreats, the boundary between high and low albedo regions shifts, creating zones of enhanced or reduced warming. Climate models must accurately represent snow extent to correctly simulate regional temperatures. The feedback between snow cover, temperature, and further snow accumulation or melting creates amplifying cycles that can accelerate warming or cooling trends. Satellite measurements of snow extent around the world track these albedo changes in real time. The white blanket of winter reshapes how Earth interacts with the sun's energy. Ice can develop layers that store decades of atmospheric chemistry. As snow accumulates and compacts into glacier ice, it traps air bubbles, dust particles, and dissolved chemicals that record atmospheric conditions at the time of snowfall, creating archives extending back hundreds of thousands of years. Scientists extract ice cores from glaciers and ice sheets, then analyze these layers to reconstruct past temperatures, atmospheric composition, volcanic activity, and forest fire histories. The trapped air bubbles contain samples of ancient atmospheres, revealing carbon dioxide and methane concentrations from long before human measurement began. Dust layers mark desert expansion events and volcanic eruptions. Isotope ratios in the ice itself indicate temperatures at the time of precipitation. The deepest ice cores from Antarctica and Greenland extend climate records back through multiple ice ages. This frozen archive continues accumulating today, recording our era for future analysis. Ice cores have transformed our understanding of Earth's climate history. Winter air can alter how food tastes and smells. The cold, dry air of winter affects our perception of food through multiple pathways, including changes in how aromatic compounds volatilize from food and how our sensory systems function in cold conditions. Volatile flavor compounds escape more slowly from cold food, reducing the intensity of aromas that contribute significantly to taste perception. Eating outdoors in winter conditions further affects taste, as cold air reduces blood flow to the tongue and nasal passages. Hot drinks and foods seem more flavorful partly because warming releases aroma compounds, and partly because warm surfaces in the mouth function more normally. Cooks and food scientists know that flavoring must be adjusted for serving temperature. Traditional winter foods often feature bold spices and strong flavors to compensate for reduced perception in cold conditions. The seasonal shift in cuisine reflects both the availability of ingredients and the altered sensory landscape. Winter changes not just what we eat, but how we experience it. Frost can grow outward from warm objects in delicate patterns. Counterintuitively, frost sometimes develops most vigorously at the edges of slightly warmed surfaces, where moisture from the warm area meets cold surrounding air and deposits as ice in delicate radiating patterns. The thermal gradient between warm center and cold edges creates conditions where moisture from the warmer zone sublimates and refreezes where temperatures drop below the dew point. This effect can create halo-like frost patterns around warm buried pipes, around the edges of imperfectly insulated windows, and wherever heat sources create temperature gradients across surfaces. The patterns reveal invisible heat flow paths that would otherwise be difficult to detect. Building inspectors use frost patterns as indicators of insulation gaps and heat leaks. The decorative effects of frost forming between warm and cold zones have inspired artists and pattern designers. Physics writes its equations in frost on cold winter surfaces. Freezing water can form column structures that look man-made. Under certain freezing conditions, ice can develop surprisingly regular columnar structures that appear too geometric to be natural, formed through processes that concentrate freezing along specific growth axes. Columnar ice, also called congelation ice, forms when water freezes slowly from a surface, with ice crystals oriented consistently and growing in parallel columns perpendicular to the cooling surface. The resulting structure shows when ice is broken, revealing sections of aligned ice prisms. Similar columnar arrangements appear in frozen waterfalls, icicles, and lake ice under certain conditions. The regularity arises from the crystal structure of ice and the physics of heat flow during freezing. Some formations resemble bundled drinking straws or organ pipes. Where groundwater seeps from hillsides and freezes, columnar ice can build up in formations resembling architectural columns. These natural ice columns demonstrate how physical laws create order from simple principles. Sea ice can host complex microbial ecosystems within brine channels. The network of salty brine channels within sea ice supports thriving communities of bacteria, algae, and small invertebrates adapted to the extreme conditions of cold, high salinity, and limited space. These brine channel ecosystems remain active throughout polar winters, with photosynthetic algae growing in channels near the ice surface where light penetrates. Bacteria decompose organic matter within the channels, cycling nutrients in miniature versions of open water ecosystems. Small invertebrates including copepods and nematodes navigate through the liquid pathways, grazing on algae and bacteria. When the ice melts in spring, these organisms seed the surrounding water with life. The productivity of polar brine communities significantly contributes to the food web that supports fish, seabirds, and marine mammals. What appears to be lifeless frozen ocean actually hosts active biological communities throughout the cold months. Sea ice is a living habitat, not merely frozen water. Frozen waterfalls can trap the sound of flowing water beneath. Waterfalls that freeze during winter often continue flowing beneath their icy exteriors, with water trickling through tubes and chambers inside the frozen structure. The sound of this hidden flow can be heard by standing near the frozen falls, a ghostly rushing muffled by ice walls. The ice exterior forms first where spray freezes on cold rock and accumulates layer by layer as splash continues feeding the growing structure. Behind this frozen curtain, warmer water from deeper sources may continue flowing, prevented from freezing completely by its constant movement. Ice caves formed behind frozen falls can be hauntingly beautiful, with blue light filtering through translucent walls while water music plays inside. The structures are inherently temporary and dangerous, as warming can cause sudden collapse. These frozen falls represent water caught mid-motion, still flowing inside its frozen shell. Frozen waterfalls are monuments to transition between liquid and solid states. Snow can convert sunlight into heat through subtle chemical reactions. While snow is famous for reflecting most incoming sunlight, a small fraction is absorbed and drives chemical reactions within the snowpack that can slightly warm the surrounding material. Nitrogen compounds, organic molecules, and other trace chemicals in snow can undergo photochemical reactions when exposed to UV light, releasing small amounts of heat. More significantly, these reactions release gases including nitrogen oxides and formaldehyde that affect local and regional air chemistry. Snow acts not just as a passive reflector, but as a photochemical reactor processing atmospheric pollutants. Dark particles such as soot and dust deposited on snow surface absorb light much more efficiently, significantly increasing local heating and accelerating melt. Even microscopic amounts of dark material can measurably affect snowmelt timing. Snow chemistry represents an active research area as scientists work to understand how snowpacks process light and pollutants. The white surface is more chemically active than its appearance suggests. Winter storms can shape sand and soil into new formations. The powerful winds of winter storms can move enormous quantities of sand, soil, and other loose material, reshaping landscapes in ways that persist long after the storms pass. Frozen ground and reduced vegetation cover during winter can expose soil to wind erosion that would not occur during growing seasons. Dust storms in winter can carry material hundreds of kilometers, depositing it on distant snow surfaces where it becomes visible as distinct layers. Coastal dunes can shift and rebuild during winter storms when off-season visitors are absent. Agricultural regions may lose topsoil to winter wind erosion if fields are left bare after harvest. The formations left behind by winter winds include ripples frozen into mud flats, wind-sculpted snow dunes called sastrugi, and eroded faces on exposed rock. Winter's atmospheric power leaves lasting signatures on the land. The cold season contributes significantly to the ongoing reshaping of Earth's surface. Cold air can reveal heat signatures invisible at warmer temperatures. The stark temperature difference between warm objects and cold winter backgrounds makes thermal imaging particularly effective during cold weather, as heated buildings, vehicles, and animals stand out dramatically against the frigid landscape. Infrared cameras that detect heat radiation produce clearer, higher contrast images when the temperature difference between subject and background increases. Search and rescue teams find missing persons more easily in winter because body heat contrasts sharply with snow and frozen ground. Energy auditors recommend conducting thermal inspections during cold weather when heat leaking from poorly insulated areas becomes most visible. Wildlife researchers use winter thermal imaging to count animals that would be invisible against warm summer landscapes. Even human vision can detect heat-related effects like rising thermals from warm rooftops, visible as shimmering air against stable cold backgrounds. The cold of winter creates contrast that reveals warmth hidden at other seasons. Cold air turns the landscape into a canvas that makes heat visible. Ice can split rock through repeated freezing cycles. The expansion of water as it freezes, exerting pressures theoretically exceeding 100 megapascals in confined spaces, can crack and split even the hardest rock when water trapped in fissures undergoes repeated freeze-thaw cycles. Each freezing event widens existing cracks slightly, allowing more water to enter and freeze on subsequent nights. Over the course of a single winter with many freeze-thaw cycles, significant rock fracturing can occur. The process is most effective when temperatures hover around freezing, allowing water to repeatedly melt, penetrate deeper into cracks, and refreeze. Mountain climbers and geologists know that frost-shattered rock fragments litter the bases of cliffs in cold climates. Ancient civilizations used this principle to quarry stone by drilling holes, filling them with water, and waiting for winter. The slow power of freezing water has shaped mountain landscapes over geological time. Ice is patient but relentless in its work of breaking stone. Winter landscapes can develop natural acoustic amplifiers. The combination of frozen surfaces, snowbanks, and cold air layers can create natural amphitheaters where sound is reflected and focused in unexpected ways, making distant sounds clearly audible or concentrating noise at particular spots. Hard frozen ground and ice reflect sound waves rather than absorbing them as soft earth and water would. Bowl-shaped terrain covered with reflective snow can focus sound waves towards certain locations. Cold air inversions that trap sound near the surface may then channel it across frozen lakes or open terrain. People have reported hearing conversations or machinery from surprising distances during still winter nights. Historic accounts mention hearing distant battles or church bells during freezing weather when sound propagation conditions aligned favorably. These natural acoustic effects have practical implications, as noise from winter activities can travel farther than expected. The frozen landscape transforms into a resonating chamber for sound. Frozen tundra can preserve ancient forests below the surface. Permafrost, ground that remains frozen throughout the year, can preserve organic material, including the remains of ancient forests for thousands of years, with tree stumps, roots, and even intact wood still present below the frozen surface. These preserved forests grew during warmer climate periods when the region supported trees, then became entombed as permafrost formed during subsequent cold periods. As climate warming thaws previously frozen ground, these ancient forests emerge, sometimes releasing preserved trees that still show growth rings and bark. The wood may be thousands of years old, yet appear freshly fallen. Scientists study these preserved forests to understand past climate conditions and vegetation patterns. The thawing also releases ancient organic matter that decomposes and releases carbon dioxide and methane. Permafrost acts as a deep freeze, preserving snapshots of past ecosystems. The frozen ground is a time capsule containing forests that last saw sunlight millennia ago. Lakes can freeze so transparently that the bottom becomes visible. Under the right conditions, lakes can develop ice so remarkably clear that the bottom, even many meters deep, becomes visible through layers of frozen water that appear almost invisible. This transparency occurs when freezing proceeds slowly and steadily without introducing air bubbles, when the water is free of suspended particles, and when no snow accumulates to obscure the surface. Such perfect conditions occur most commonly on calm, cold nights over clean lakes in protected locations. The effect can be disorienting, as the ice surface becomes nearly invisible and the bottom appears to be directly beneath one's feet with nothing in between. Photographs of people appearing to stand on clear floors above visible lake beds have circulated widely for their surreal quality. The transparency reveals fish, underwater vegetation, and bottom structures normally hidden from view. These windows of ice offer rare glimpses into winter underwater worlds. Snow lines across mountains can map wind currents precisely. The patterns of snow accumulation and removal across mountain slopes reveal the invisible architecture of wind flow, with snow lines, drifts, and bare patches forming maps of how air moves across complex terrain. Windward slopes facing prevailing winds accumulate snow where wind slows and deposits its burden of precipitation. Leeward slopes may be swept clean by accelerating wind or accumulate massive cornices where wind decelerates after passing ridges. Gullies and valleys can channel wind, creating distinctive patterns of snow accumulation that repeat year after year. Experienced mountaineers read these snow patterns to understand local wind conditions and avalanche risk. Scientists use aerial photography of snow distribution to study airflow patterns that would be difficult to measure directly. The patterns change as winds shift directions seasonally. Snow distribution becomes a visible language that translates invisible air movements into readable patterns. Winter storms can temporarily rearrange ocean layers. The powerful winds and waves of winter storms can mix ocean waters that normally layer by temperature and salinity, temporarily disrupting stratification and bringing nutrients from the depths toward the surface. During quiet conditions, oceans develop stable layers with warmer, less dense water floating above colder, denser deep water. Storm energy breaks down this stratification by physically mixing surface and deeper waters. The mixing brings nutrients that have accumulated in the dark depths up toward the sunlit zone where photosynthesis occurs. This nutrient injection can trigger plankton blooms once the storm passes and light returns. Winter storms thus play an important role in the biological productivity of ocean ecosystems. The effects of mixing may persist for weeks after storms pass, as restratification takes time. Violent surface conditions connect to the hidden processes that support marine food webs. Ice can grow in feathers and fans instead of solid sheets. When conditions favor rapid crystal growth along certain axes, ice can develop in elaborate branching patterns resembling feathers, fans, or ferns, rather than forming the solid sheets typical of frozen ponds and lakes. Feather ice is particularly common on ice cave ceilings where moisture sublimates and refreezes, growing downward in intricate crystalline plumes. Similar branching patterns develop on windows when humidity and temperature conditions promote rapid growth. The physics favoring branching growth relates to how heat is removed during freezing, as projecting crystal tips cool faster and grow more rapidly than flat surfaces. These delicate structures are easily damaged by touch or change in conditions. Ice flowers that grow on young sea ice demonstrate similar branching tendencies. The feathered and fanned forms represent ice expressing its crystalline nature rather than simply filling space. When given opportunity, ice grows in forms that reveal its internal geometry. Winter conditions can dramatically change how animals communicate. Snow cover, cold air, and reduced vegetation during winter alter the acoustic environment significantly, forcing many animals to adjust their vocalizations and communication methods to remain effective. Sound travels farther and more clearly through cold, stable winter air, meaning that territorial calls and mating songs may need less energy to reach distant listeners. Snow cover absorbs high frequencies preferentially, requiring some animals to shift toward lower-pitched calls. Birds that sing from leafy perches in summer must find different strategies when bare branches offer little acoustic benefit. The crunch of snow underfoot forces predators to develop new stalking techniques and prey to listen for different warning sounds. Some animals communicate more by scent during winter when food caches must be defended. Visual signals become more effective against simplified white backgrounds. Winter transforms the communication landscape as thoroughly as it transforms the physical one. Snow cover near cities can shift local temperatures measurably. Snow-covered areas around cities, compared to the snow-free pavement and buildings of urban centers, create measurable temperature differences that demonstrate the thermal effects of surface reflectivity and the urban heat island phenomenon. Cities without snow cover absorb solar energy during the day and release stored heat at night, remaining warmer than surrounding natural areas. Adjacent snow-covered parks, suburban areas, or surrounding countryside reflect more sunlight and stay cooler, amplifying the urban-rural temperature contrast. Satellite temperature measurements clearly show this effect, with urban areas appearing as warm islands surrounded by cooler snow-covered terrain. The difference affects local wind patterns, with air flowing from cool suburbs toward warm centers. Snow removal decisions in cities have thermal consequences beyond simple convenience. Understanding these effects helps urban planners manage heat in both summer and winter. Snow becomes a tool for measuring how cities modify their own climates. Frozen air can create visible shock waves around moving objects. In extremely cold conditions, the air becomes dense enough that shock waves produced by fast-moving objects can sometimes become visible, with compression waves appearing as brief disturbances around aircraft, projectiles, or even cracking whips. These shock waves occur whenever an object moves faster than the local speed of sound, which decreases as air temperature drops. At extremely low temperatures, the speed of sound may drop below 300 meters per second, making sonic effects more likely at lower speeds. Visible shock waves appear as condensation forms briefly in the pressure changes associated with the compression. Photographers have captured these effects around aircraft in cold conditions, showing the invisible made temporarily visible. Even subsonic objects can create visible pressure waves in sufficiently cold, humid air. The physics of sound and compression become more apparent when cold air responds more visibly to disturbance. The cold air makes normally invisible acoustic phenomena momentarily visible. Winter fog can become so cold that it forms crystals midair. Ice fog forms when temperatures drop below approximately -30 degrees Celsius and humidity remains sufficient for water vapor to freeze directly into tiny ice crystals that remain suspended in the air. Unlike ordinary fog composed of liquid water droplets, ice fog consists of microscopic ice particles that glitter in sunlight and create distinctive optical effects. Ice fog is most common near open water in Arctic regions, where evaporating water provides moisture that immediately freezes in the surrounding frigid air. Human activity can create ice fog through vehicle exhausts, power plant emissions, and even the moisture from breathing, which adds water vapor that rapidly freezes. The particles are so small and light that they remain suspended for extended periods. Ice fog can persist even when conditions would dissipate liquid fog. Walking through ice fog creates the sensation of moving through a cloud of frozen diamond dust. This frozen version of fog transforms the ordinary phenomenon into something extraordinary. Frozen ocean waves can store energy that releases when thawed. When ocean waves freeze in place, the ice structure that forms can store mechanical stress and potential energy that releases suddenly when the ice eventually melts or fractures. Sea ice forming in rough conditions captures the shapes of waves and swells, locking that geometry into solid form. The ice may shift as subsequent freezing and refreezing occurs, building up internal stresses. Tidal movements beneath coastal ice create additional mechanical stress as rigid ice is repeatedly flexed. When spring warming begins, the stored stresses can cause dramatic ice breakup, with ice fracturing and piling up in spectacular fashion. The energy released during breakup events can reshape shorelines and damage structures. Coastal communities in cold regions must account for the power stored in winter ice when it finally releases. The frozen sea stores the energy of winter storms, releasing it all at once when conditions change. Winter skies can generate extremely rare atmospheric arcs. The ice crystals suspended in cold winter air can create optical phenomena beyond common halos, including rare arcs, circles, and light columns that appear only when crystal shapes, orientations, and sun angles align precisely. Some of these phenomena appear only a few times in a lifetime, even for dedicated observers. Superlateral arcs, periarcs, and circumhorizontal arcs each require specific crystal geometries and sun positions. Multiple rare arcs occasionally appear together in complex displays that have been documented and studied since antiquity. The more exotic optical phenomena typically occur in polar or subpolar regions where appropriate ice crystals are most common. Photographers and atmospheric scientists travel to witness and document rare optical shows when conditions seem favorable. Each archetype reveals information about the ice crystals that create it. Winter's gallery of atmospheric optics extends far beyond the common ring around the moon. The rarest optical phenomena turn winter skies into physics laboratories. Snow depth can determine where entire species migrate. For many animals, the depth of snow cover directly influences whether they can access food, travel efficiently, or survive predation, making snow conditions a primary factor determining where populations concentrate during winter months. Ungulates like elk and deer move to lower elevations where snow is shallower and vegetation remains accessible. Deep snow can trap smaller animals, while the same depth poses no barrier to larger species, creating zones where only certain animals can thrive. Predators follow their prey, so migration patterns of herbivores drive movements of the entire food web. Birds that feed on ground-dwelling insects or seeds must relocate when deep snow covers their food sources. Snow crusts that form after thawing and refreezing can support some species while trapping others. Wildlife managers monitor snow conditions as carefully as they monitor animal populations. Snow depth acts as an invisible barrier that sorts species across the landscape. Frozen ground can shape river paths long before spring thaw. When soil and riverbanks freeze solid during winter, they resist the erosive forces that would normally reshape watercourses. Frozen banks hold their form even against flowing water, while unfrozen sections erode more readily. Rivers may develop new curves and channels preferentially where frozen ground provides less resistance. Groundwater springs that prevent complete freezing create weak points where erosion concentrates. The eventual spring thaw releases the rigid structure all at once, sometimes causing banks to collapse or rivers to suddenly change course. Ice jams that form at frozen bends can redirect flow and carve new channels when the jam releases. Engineers designing in cold climates must account for these winter-spring transitions. The rigid winter riverbank stores potential change that expresses itself dramatically in spring. Frozen ground controls rivers during winter and shapes the changes that appear when warmth returns. Winter storms leave behind patterns that map their path. The debris, deposits, and erosion patterns left by winter storms create readable records of wind speed, direction, and progression that scientists and observers use to reconstruct storm behavior after the event passes. Snow drifts point downwind, revealing prevailing wind directions during the storm. Branch damage in forests traces the path of strongest winds. Ice accumulation on different sides of structures shows which direction the freezing precipitation approached from. Debris carried by flooding from snowmelt concentrates along the paths that water followed. These patterns remain visible for days or weeks after events, allowing detailed analysis of storms that lasted only hours. Insurance, adjusters, and meteorologists use damage patterns to estimate wind speeds. The landscape becomes a record of atmospheric violence, written in snow, ice, and debris. Each major winter storm writes its signature across the terrain for those who know how to read it. Ice can form double layers with different properties. Lakes and bodies of water can develop layered ice structures where ice formed under different conditions creates distinct zones with differing transparency, strength, and other properties. Early season ice formed on calm water may be clear and strong, covered by later ice that formed from flooded snow or during turbulent conditions, which tends to be white and weaker. These layers can separate, creating hazardous conditions where apparently thick ice contains weak zones. Repeated flooding of the surface by water welling up through cracks or from melting snow can create multiple alternating layers. Ice fishers and winter travelers learn to recognize different ice types and their implications for safety. The clear black ice of early freeze is prized for its strength, while white snow ice is viewed with more caution. Ice cores reveal the history of freezing conditions layer by layer. Each ice layer tells a story of the conditions under which it formed. Snow blankets can hide volcanic gases until they melt. Volcanic regions that experience snow cover can trap volcanic gases beneath the snowpack, concentrating them in hollows and depressions where they may accumulate to dangerous levels until melting releases them. Carbon dioxide and hydrogen sulfide emitted by volcanic vents are denser than air and tend to collect in low-lying areas, where snow cover can trap them by blocking dispersal. Animals and people entering these gas-filled pockets can lose consciousness from oxygen displacement or poisoning. The hazard increases during snowmelt, when gas that accumulated over winter suddenly releases as snow cover thins. Monitoring stations at active volcanic areas track gas concentrations throughout the year. Indoor spaces built on volcanic ground can accumulate gases that infiltrate through foundations, especially during periods of high snow cover. The beautiful snow covering volcanic terrain conceals invisible hazards. Winter adds complexity to the already challenging task of living near active volcanic systems. Frozen lakes can amplify vibrations from miles away. The ice sheet covering a frozen lake can act as a resonating membrane that transmits and amplifies vibrations from distant sources, making the ice respond to disturbances kilometers away as if they were much closer. Walking on lake ice can produce booming sounds audible across the entire lake as the ice flexes in response to weight. Distant thunder or even seismic events can set an entire lake of ice vibrating. The sounds produced range from deep booming to eerie singing tones as the ice oscillates at its natural frequencies. Ice fishers positioned quietly can sometimes hear conversations from the opposite shore of a lake, carried and amplified by the resonant ice. Wind can set ice sheets vibrating with sustained tones. Scientists use these acoustic properties to study ice thickness and structure by analyzing how the ice responds to controlled vibrations. A frozen lake becomes a giant drum, resonating with the winter world. Winter pressure changes can alter animal behavior noticeably. The atmospheric pressure changes associated with approaching winter storms can trigger behavioral shifts in many animals, which appear to sense and respond to pressure drops before other weather signs become apparent. Birds may feed more intensively before storms, building energy reserves knowing that foraging will become difficult. Fish activity patterns change with pressure shifts, a phenomenon well known to anglers who track barometric readings. Deer and cattle often become restless before pressure drops, moving to shelter or changing feeding patterns. Joints and old injuries in humans also respond to pressure changes, lending credence to folk beliefs about weather prediction through body sensations. The sensitivity of some animals to pressure changes may relate to air bladders, sinuses, or pressure-sensitive sensory cells. These responses have practical value, as eating before a storm or seeking shelter improves survival odds. Animals read the atmosphere continuously, responding to invisible signals that humans are less sensitive to. Freezing temperatures can make wood behave almost like metal. When the water within wood freezes completely, the material becomes dramatically harder and stronger, approaching some properties of metal and requiring very different handling than unfrozen timber. The ice crystals forming in wood cells and fibers essentially create a composite material with ice acting as a structural element. Cutting and machining frozen wood requires sharper tools, more power, and different techniques than working with unfrozen material. Historically, loggers preferred to harvest timber in deep winter when frozen logs were easier to skid across snow and ice. The transition between frozen and thawed states must be managed carefully to prevent checking and cracking as ice crystals melt. Instruments made from wood must be allowed to warm gradually to avoid damage from rapid expansion. The strength increase can be beneficial, with temporary frozen wood structures serving until thaw. Winter transforms the familiar properties of wood into something its warm weather form would not predict. Winter cold can lock minerals into place in ways summer cannot. The freezing of soil water locks mineral particles in place, halting the chemical and physical processes that would otherwise move and transform soil minerals during warmer months. Chemical weathering reactions proceed much more slowly or stop entirely when temperatures drop below freezing. Clay particles that would swell and shift with changing moisture become rigid. Metal objects buried in frozen ground remain remarkably stable compared to their movement in unfrozen soil. Archaeological sites in permafrost regions preserve metal artifacts better than warmer climates where electrochemical corrosion proceeds throughout the year. The freezing of pore water essentially pauses the geological processes that gradually alter mineral assemblages. Some industrial processes exploit this effect by freezing ground to stabilize excavations. The cold creates a pause in the ceaseless chemical activity of Earth's surface. Winter's freeze button temporarily halts the molecular motion that transforms landscapes over geological time. Snowfall rates can increase sharply with tiny temperature shifts. The relationship between temperature and snowfall is not linear, with the most intense snowfalls occurring within a narrow temperature range just below freezing, where air can hold relatively high moisture levels. A slight temperature drop from just above to just below freezing can trigger sudden transition from rain to heavy snow. At temperatures well below freezing, the air becomes too dry to hold much moisture, limiting snowfall totals even during extended events. The heaviest snowfall events typically occur when temperatures hover just below the freezing point, while abundant moisture is available. Weather forecasters monitor temperature profiles carefully because a degree or two makes the difference between rain, heavy snow, or light snow. The sensitive dependence on temperature makes winter precipitation forecasting challenging. Cities near the rain-snow transition zone may receive dramatically different precipitation types despite being close together. Small temperature shifts create large differences in winter precipitation outcomes. Frozen soil can heat upward through narrow channels. In frozen ground with unfrozen zones beneath, heat can flow upward through channels and pipes, creating localized warm spots where the thermal pathway penetrates the frozen layer. Groundwater springs that remain liquid provide obvious pathways, but even dry soil can conduct heat differently based on mineral content and structure. The surface above these warm channels may remain snow-free, while surrounding areas are covered, revealing the hidden thermal pathways. Buildings can create similar effects, with heat leaking into the ground and reaching the surface along preferred pathways. Utility lines, even when not actively heated, can create pathways that conduct warmth upward from deeper unfrozen zones. The patterns visible at the surface provide clues about subsurface structure and heat flow. Infrared imaging reveals these warm spots even more clearly than snow patterns. The frozen surface becomes a screen showing the hidden thermal activity beneath. Ice can preserve footprints for an entire season. Tracks made in wet mud, sand, or soft ground that subsequently freezes can remain preserved throughout the winter, lasting months longer than they would in unfrozen material, where weathering and biological activity would quickly obscure them. Snow covering the frozen tracks provides additional protection, and tracks may emerge again intact after spring melt. Wildlife biologists use winter track preservation to study animal movements and population estimates. Crime scene investigators know that footprint evidence can persist much longer in frozen conditions. The detail preserved in frozen tracks often exceeds what would survive in any other conditions, including fine tread patterns and size measurements. Ancient tracks have been frozen in permafrost for thousands of years. The freezing process creates casts that can be studied with techniques similar to fossil footprint analysis. Every step taken on the threshold of winter may be recorded until spring arrives. Winter storms can collect atmospheric dust that would otherwise disperse. Snowflakes falling through the atmosphere are remarkably effective at capturing tiny particles including dust, pollen, spores, and industrial emissions, bringing them to ground far more efficiently than rain and concentrating them in the snowpack. Each snowflake grows by collecting water vapor, and its intricate structure with large surface area also sweeps through and captures solid particles. Snow acts as an atmospheric filter, cleaning the air but concentrating particles where the snow accumulates. Spring melt releases these collected particles, sometimes visibly dirtying the remaining snow. Scientists sample snowpacks to measure atmospheric pollution loads and track the movement of dust from distant deserts or volcanic events. Radioactive fallout from nuclear tests was tracked through snow sampling in polar regions. The annual snowpack becomes an archive of atmospheric particles deposited throughout the winter. What falls as white snow carries with it a chemical record of the air it passed through. Frozen vegetation can act as natural fiber optics for sunlight. The ice crystals that form on bare branches, grass stems, and leaf surfaces during freezing fog events can transmit and redirect sunlight along the frozen structure, creating effects similar to fiber optic transmission, where light travels along curved paths within transparent material. The ice layer acts as a cladding that keeps light bouncing internally along the ice-covered stem or branch. This effect can be observed when frost-covered vegetation seems to glow from within as light enters at one point and emerges elsewhere. The transparent ice coating conducts light around curves and bends. Scientists have studied these natural light guides as models for understanding optical transmission in irregular structures. The ethereal appearance of frost-covered landscapes at dawn partly results from this light-guiding effect. Each ice-covered twig becomes a tiny light pipe conducting sunrise colors. Winter frost turns ordinary plants into networks of glowing filaments. Snow cover can alter the path of groundwater beneath. The insulating effect of snow cover prevents deep soil freezing, which in turn affects where groundwater can flow during winter and thus which springs remain active and which freeze shut. Areas of deep snow may have unfrozen soil, allowing continued groundwater movement, while bare areas freeze deeply and block flow. This creates patterns where groundwater emerges at the edges of snow-covered zones, following paths determined by the snowpack above. Springs may shift location between years depending on snow distribution. The effect matters for water supplies in rural areas that depend on spring water. Wildlife that depends on open water must find areas where snow insulation has kept springs flowing. Changes in snow distribution patterns with climate warming alter these groundwater pathways. The snowpack on the surface directs invisible water movement far below. Snow cover determines which underground channels remain open through winter. Winter can cause metals to contract enough to change mechanical systems. The thermal contraction of metal components in cold weather can alter the function of mechanical systems, change the fit of precision assemblies, and even cause structural failures when different materials contract at different rates. Steel contracts approximately 1/100% per degree Celsius, meaning a 1 meter steel beam shortens by about 1 millimeter per 100-degree temperature drop. Bridges and buildings include expansion joints to accommodate this movement. Railway tracks that were precisely fitted in summer may pull apart or buckle as temperatures change. Precision machinery calibrated in warm workshops may perform differently in cold environments. Different metals contract at different rates, causing stresses in composite assemblies. Fasteners may loosen as the bolt contracts more than the materials it clamps. Understanding thermal expansion and contraction is essential for cold weather engineering. The invisible shrinking of metal in winter affects machines in countless subtle ways. Ice sheets can generate vibrations resembling deep ocean sounds. Large ice sheets and glaciers produce low-frequency vibrations through internal cracking, calving events, and movement over bedrock that can resemble the sounds produced by marine life or geological processes in the deep ocean. These icequakes are typically below the range of human hearing, but can be recorded and analyzed by seismometers. The rumbling, creaking, and groaning of moving ice can sometimes be heard directly when ice activity is particularly high. Some recorded ice vibrations, when sped up to audible frequencies, sound remarkably like whale songs or underwater echoes. Scientists monitoring ice sheets use these acoustic signatures to track ice movement and stability remotely. The vibrations travel through rock, water, and air, carrying information about ice processes across large distances. Ice sheets have their own voices, speaking in frequencies usually too deep for human ears. The frozen landscape produces an ongoing symphony just beyond the edge of our perception. Snow can sublimate directly into the air without melting. Under conditions of low humidity and strong solar radiation, snow can transform directly from solid ice to water vapor without passing through the liquid state, a process called sublimation that can remove significant amounts of snowpack even when temperatures remain below freezing. Sublimation is most active in dry continental climates with clear skies where sunlight provides energy while dry air rapidly absorbs the resulting vapor. Mountain snowpacks can lose substantial depth to sublimation during dry spells, reducing water available for spring runoff. The process proceeds most rapidly from snow crystal tips and edges, gradually eroding detailed snowflake structures into rounded grains. Wind increases sublimation by constantly exposing fresh surfaces and carrying away vapor. Snow that appears stable can disappear surprisingly quickly without any visible melting. Water managers must account for sublimation losses when predicting water supplies from mountain snowpacks. The snow vanishes into thin air, skipping the liquid stage entirely. Frozen landscapes can create sudden cold air sinks that move downhill. Cold air is denser than warm air and will flow downhill like an invisible fluid, pooling in valleys and low-lying areas to create frost pockets that can be dramatically colder than surrounding higher ground. These cold air drainage flows occur most strongly on clear, calm nights when radiative cooling at the surface chills the air in contact with the ground. The resulting dense air slides downhill, sometimes quite rapidly, pooling wherever the terrain creates basins or hollows. Temperature differences of 10 degrees or more can separate valley bottoms from hillsides just 100 meters higher. Orchards and gardens planted in frost pockets suffer damage that would not occur on adjacent slopes. Buildings in valley locations may require more heating than those on hillsides. Fog often forms first in these cold pools where air reaches its dew point. The invisible rivers of cold air flowing downhill reshape the microclimate of every hillside. Snowpack chemistry can change based on tiny differences in sunlight. The angle, intensity, and spectral composition of sunlight reaching snowpack surfaces affects the rates of photochemical reactions within the snow, creating chemical variations between sunny and shaded slopes and between north-facing and south-facing exposures. Ultraviolet light drives many important snow chemistry reactions, including the breakdown of nitrogen compounds and the formation of reactive gases. South-facing slopes receiving more intense sunlight may develop different chemical profiles than north-facing slopes in shadow. The timing of sunrise and sunset affects which chemicals accumulate during dark periods and which are destroyed by photochemistry during daylight. Snow under forest canopy, receiving filtered and reduced light, develops differently than snow in open clearings. These subtle chemical differences may affect what organisms can live in and on the snow. The photochemistry of snow represents an active research area with implications for air quality and nutrient cycling. Sunlight constantly rewrites the chemistry of winter's white surface. Frozen lakes can crack along perfect geometric lines. As ice on lakes expands and contracts with temperature changes, the resulting stress fractures often follow remarkably straight or geometric paths, creating patterns of surprising regularity across the frozen surface. The cracks propagate at hundreds of meters per second, too fast for irregularities in the ice to deflect them, resulting in straight lines that may extend for kilometers. Where multiple cracks intersect, they often meet at predictable angles based on the physics of fracture propagation. The visual effect can resemble intentional design, as if someone drew lines across the frozen surface with a ruler. These geometric crack patterns have inspired artists and provide scientists with information about ice properties and stress distributions. The distinctive sounds of cracking ice, from pings to booms, accompany the formation of these patterns. The ice sheet records its internal stresses in a language of straight lines and predictable angles. Perfect geometry emerges spontaneously from the physics of freezing water. Winter conditions can determine which seeds survive underground. Many seeds require exposure to cold temperatures before they will germinate, a process called stratification, while other seeds are killed by freezing. Thus, winter conditions strongly influence which plants successfully reproduce in a given year. Cold stratification breaks dormancy mechanisms that prevent seeds from germinating at the wrong time, ensuring sprouts emerge in spring when conditions favor growth. Some species require multiple freeze-thaw cycles, while others need sustained cold periods. Snow cover affects seed survival both by providing insulation against extreme cold and by creating conditions for successful stratification. Seeds that lie above the snow line may freeze lethally, while those beneath the insulating layer survive. The timing and character of winter weather thus determines which seeds in the soil bank will germinate when spring arrives. Horticulturists simulate stratification by refrigerating seeds before planting. Winter selects the next generation of plants based on where and when seeds were deposited. Clear ice can form lenses capable of focusing sunlight. Very clear ice, particularly rounded pieces shaped by melting and refreezing, can focus sunlight like a glass lens, concentrating light enough to potentially start fires or cause burns, demonstrating the same optical principles used in magnifying glasses. Traditional Arctic cultures reportedly used ice lenses to start fires or for magnification. The effect requires ice of exceptional clarity and appropriate curvature, conditions that occur naturally in some circumstances. Icicles with rounded tips, ice bubbles, and ice shaped by flowing water can all develop lens-like properties. Photographers have captured images made through natural ice lenses. The focusing effect can be observed by the bright spot of concentrated light projected onto surfaces beneath the ice. Water's optical properties are similar to glass, making good ice a reasonable approximation of conventional lens material. Ice formed from the transparent parent material of water can bend light into focused points of heat and brightness. Winter air can reveal hidden heat lecks in buildings and terrain. On cold days, thermal imaging cameras or simply observing snow melt patterns can reveal where heat escapes from buildings, underground pipes, or geological features in ways invisible during warmer weather. Snow melts first over leaky basements, under-insulated rooflines, and buried steam pipes, creating visible maps of hidden heat flow. Thermal cameras show temperature differences of a fraction of a degree, making heat leaks glow against cold backgrounds. Energy auditors prefer to conduct inspections during cold weather when the temperature contrast makes inefficiencies most visible. Buried cables and pipes appear as lines of warmth in thermal images of frozen ground. Hot springs and volcanic features reveal themselves through patterns in snow cover. Wildlife sometimes betrays the location of underground dens through melted patches above their warm breath and bodies. Cold weather provides contrast that turns entire landscapes into thermal maps. Winter temperatures can alter water density to protect aquatic life. Water reaches its maximum density at approximately 4 degrees Celsius, meaning that colder water near freezing actually rises rather than sinking, creating an inverted temperature gradient that keeps the densest, warmest water at lake bottoms where fish and other aquatic life overwinter. This unusual property of water prevents lakes from freezing from the bottom up, which would kill most aquatic organisms. Ice floating on the surface insulates the water below, slowing further heat loss. Fish and other creatures survive in the relatively warm water near the bottom, while ice seals the surface above. If water behaved like most liquids, with coldest water being densest, lakes would freeze solid from bottom to top, making winter survival impossible for most aquatic life. The anomalous expansion of water near its freezing point is one of water's most important properties for life on Earth. Physics creates a sanctuary for aquatic life beneath the frozen surface. Frozen clouds can drift for long periods without producing snow. High-altitude clouds composed entirely of ice crystals may persist for days or weeks without producing precipitation that reaches the ground, as the tiny crystals are too light to fall through the atmosphere at significant rates. These cirrus and cirrostratus clouds form from ice crystals that grow very slowly in the thin air of the upper troposphere. Individual crystals may be settling downward continuously, but sublimation in lower, warmer air destroys them before they reach the surface. The clouds appear to simply float, neither growing much nor dissipating, maintained in a balance between formation and loss. Their persistence affects climate by scattering some incoming sunlight while trapping some outgoing infrared radiation. The net effect on temperature depends on cloud thickness, height, and crystal properties. These frozen veils across the sky play subtle but significant roles in Earth's energy balance. Frozen clouds demonstrate that what appears static may actually be in continuous dynamic equilibrium. And now the quiet wonders of winter begin to gently fade into the stillness of the night. You have wandered through over 100 peaceful truths about the coldest season, from the delicate geometry of snowflakes to the deep sounds of frozen lakes, from creatures that survive by letting their bodies freeze to the hidden ecosystems thriving beneath the snow, from storms that flash with lightning through swirling white to the ancient secrets preserved within glacial ice. You have explored how winter reshapes landscapes, how cold transforms materials, how sound travels farther through frigid air, and how so much life adapts to survive the harshest conditions. You have learned that beneath the frozen surface, there are layers upon layers of wonder. You are connected to this story more deeply than you may realize. Right now, as you listen, winter is at work somewhere on Earth. Snow is falling silently, ice is forming, lakes are creaking in the darkness. The work of the cold continues without pause, as it has for billions of years. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the quiet drift of snowflakes, like the gentle hum of a frozen world at rest. Tonight, as you rest, winter continues its quiet work. It will guard its secrets, shape its crystals, preserve its ancient records, cool the air, and wait patiently for the seasons to turn once more. You are a small, warm presence within this vast frozen world, peacefully resting among the wonders. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that you are never truly alone, for winter is always somewhere on Earth, quietly at work, shaping the world in ways both seen and unseen. Thank you for joining me on this journey through the mysteries of winter. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of the natural world. There are more wonders waiting, more secrets hidden in the frost and the quiet corners of frozen landscapes, more gentle truths to drift through on quiet evenings. Rest well, and may the gentle stillness of winter keep you company.